So let's welcome Iacopo Longarini. So Iacopo got his PhD in 2022 in experimental particle physics at Sapienza University in Rome. He is now a postdoctoral researcher in particle physics at the University of California, Irvine. He is a member of the Atlas collaboration, where he works on beyond standard model physics searches and on the L0 MDT trigger for phase 2 upgrade of Atlas experiment. So he's going to present the Spybuffers. The floor is yours.
Thanks a lot for the introduction. You can see the title here of the talk, just to checking that this is working correctly. And I wanted to say a big thank you to Priya and to Benjamin, because they contributed a lot, especially in the HDL development, the early validation and the testings of what is being what I will present in a moment. So a little bit of introduction to the fast monitoring. And the fast monitoring is a concept that helps in doing real-time debugging of FPGA firmware, and also giving some high-level information when errors are detected, or providing quality control during the operation of your device. Forgive me if I will be saying firmware erroneously, but maybe gateware would be a more appropriate word, but for the moment, forgive me, please. But I want to say that the basic building block is the Spybuffer, which is denoted as this little magnifying lens here, also on the schematic that we have here on the right. And the Spybuffers can be placed at the input or at the output of several firmware blocks, for instance, to spy or monitor, using more appropriate terms, what is being passed through the data path of your FPGA, so what is being processed by your algorithm. And ideally, the content of the Spybuffer can be accessed via the control path, so via some special channel, which is then talking to a service which, for instance, can run on an SoC, but you can have also several other interfaces as an alternative to this. The interesting part is that this is not only for spying or monitoring the data path, is also for injecting data. And the purpose is that with this you can enable some advanced debugging or reproduction of issues and some other things that I'm going to talk about in a moment. Just to say that the Spybuffer are controlled by some specific block, which is this FM controller. We'll talk about it in a moment. But this needs to be implemented in the firmware because it's highly dependent on the implementation of the rest of the algorithms. And there are implementation of Verilogs in Verilog and software resources at this repository here. So a little bit more into detail about the Spybuffer itself. This is an object that is supposed to be sitting between two logic blocks, and normally your data path will be from A to B. So the Spybuffer is just a small HDL core, and this is essentially taking a copy of all the incoming data from A, and which is also being sent through as a copy to a circular buffer. And at the same time, this is passed to the logic block B, so without interrupting the flux of data between those two objects. And eventually, if you need, for instance, some clock domain transition or some busy logic, you can also add a FIFO, which is the configuration for that is shipped together with the HDL core. The interesting part is where you can actually run some interaction with the memory of the Spybuffer, because as I was saying, this is a circular buffer that is constantly written, and you can issue from your SoC, for instance, the freeze command, and this will tell the memory to stop writing everything that is incoming from A. But at the same time, what will be sent from A to B, in principle, would be occurring without any issue. So after the freeze signal, what is transmitted from A to B is uninterrupted, but the monitoring is stopped. So at some point, if your memory here is memory mapped, you can access it and you can read the content to get a snapshot in time of what was being sent through your data path. Another interesting approach, another interesting mode is the playback mode. So assuming that you already froze your Spybuffer, so its memory is not being written anymore by what is incoming from the logic block A, then you can write something that you maybe have from simulation, or maybe something that you want to test, some logic that you want to test, some test words that you want to test. And when you act on the playback signal, the multiplexer that is here will act on the, will act on the data path, replacing the content from what is coming from A with the content of the memory. And this can be done in a playback once mode, so that is just done once and then it waits for the user interaction, or with a playback loop, so that this is repeated continuously. If I go a little bit more into the details of how this is implemented and how this has to be interfaced, so as I mentioned, the Spybuffer can support up to 3 different clock domains. And in this case, this is for the case in which the dual clock FIFO is added in the data path. So in the little diagram here, you have all the connections for this IP, and the one that are corresponding to the data path are this. You can have the 2 different the controls for the FIFO, the information about the for instance empty or almost full, and you have write clock and read clock domain. On the other hand, you have the spy clock domain, which maybe is different from the one of your data path, and this gives you all the interfaces from your slow clock through the memory. I'm saying slow for a reason, because you would expect that if you use this in a logic, at least I'm saying this with the mind of a person that works in a high energy physics experiment, this would be like the fast clock, and this would be a slower clock for monitoring. But to mention a few of the parameters that are needed in order to configure this, you can configure the width of the data in the data path on the 2 sides, and also the width on the control path, because this is maybe not the same depending on your interface. And at the same time, you can set the address width, so how deep is your memory from this point of view. And last, there is this pass-through option, which is essentially controlling if the FIFO is inserted or not. In this case, there are 4 clock cycles that are added as an additional latency by minimum. If I wanted to show a little bit the example of the waveforms. Unfortunately, this was supposed to be animated, but I must have done something wrong when exporting the file. Apologies for that. But you can see here that so on the bottom part, there is the control path, while the upper part above this signal highlighted in yellow, I hope that this is clearly visible for everybody, is the data path. What I wanted to highlight is that in the region that are marked in yellow, in this part, the signal that is corresponding to the freeze mode is set to 1, also here and here. And, oops, I was supposed to be on the slide. But I mean, for what I mentioned, is the same. And in this case, you can see that, for instance, this is showing the freeze mode. So when you have some transactions that are occurring on the data path, but the data path is being written without issues. What is being written to the Spybuffer is also being read from interface B, but at the same time, the spy memory is not being written. And that means that if you are in this situation, you can read, and you can see, for instance, in this other example, we have the readout from the control path, where you see all the read transactions here. Sorry, I have to highlight them, but because maybe this is a little bit too tiny. But it's showing how essentially the data path is not interrupted and the spy memory is not written. On the other hand, with the playback mode, we start from a configuration in which the Spybuffer is frozen. We write data to the Spybuffer, so you have the transactions on the control path. And then this data is being read from the Spybuffer memory during the playback phase, and it's being at the same time written to the second interface in a way that you are injecting data through the path or through your firmware. At the same time, you can do this, as I mentioned before, once or in a loop. I mean, it's not very clear here from the screenshot, but it gives the idea. The implementation and resource usages of this, of course, depend on many parameters, but mostly from how many Spybuffer you need to implement, depending on the application, the width and depth, and this can depend on how many consecutive hit entries you want to keep. For instance, you can imagine that these are events that are coming at a very high rate, and you want to keep a given number of bunch crossings. So then you have to, according to your logic, you have to regulate the depth of your Spybuffer in this way. But the Spybuffer itself is something that is technology independent. It has been written in Verilog, and it doesn't need vendor-specific IP. And the synthesis tool, when there are, for instance, for the Spybuffer memories, these are implemented in RTL, so the synthesis can just optimize the implementation based on what your FPGA has. And the thing that I mentioned at the beginning was the control block. And this is really something that is very tied to the implementation of your firmware. Because you can imagine that if you have just one Spybuffer, you don't need this control block. You just access the interfaces. If you have multiple ones, you need maybe to have, as in this case, as in this example that I will refer also later, you will have global control signal, so a global freeze and a global playback signal that is connected to all the Spybuffer, but then you can have a masking system to just act on which Spybuffer are responding to this signal. And this is exactly what is used in the examples that I have in the rest of the presentation. And because I wanted to mention a little software module which is used for interacting with Spybuffer. And this has been tested, for instance, with an SoC accessing the firmware register on another FPGA via the AXI chip-to-chip link. And there is a Python module which is named, which is linked in the same repository that I linked before. And this has been developed to just simplify this interaction, and it's based on IP bus that we mentioned also before. So I will not spend a lot of time on that, but IP bus gives microHAL, which is providing a useful C++, but mostly useful for this case, the Python API for I/O operation on memory mapped registers. And for that, you need to configure it with registers that are written, for instance, in this way, with an XML file that is showing here the configuration. So here we have all the control registers, all the global freeze and playback mode. Here we have masks that are determining how many Spybuffer we can have and we can control. So in this case, we have 32 bits times 2, so this would be 64 Spybuffers at most. And here I have just 2 Spybuffer that are memory mapped, which are named dummy1 and dummy0 for the example that I will have in a few slides. So I was mentioning the software. As I was mentioning, the software is just to simplify the interaction, and in principle it relaxes all the consecutive commands that you want to do on the Spybuffer. So for instance, you can set the playback mode, and this will take care of all the masking and all the things that are needed behind. So if you need, for instance, to write a Spybuffer and you need to do some resizing of the data, this is also taking care of that. And essentially, they want to remove all the dependencies of all the interaction with the single register, especially the global control ones. In this way, we can just write a simple Python script, and this will test your firmware, for instance, in one of the ways that I will mention in a couple slides, because I want to move to the use case. And so first use cases, you have some partial logic block that has been developed. This can be already implemented, but maybe not all the blocks of your gateway are implemented. So the Spybuffer can be placed at one of the 2 ends in order to emulate the missing ones. This can be used this can have some application of this kind. But also at the same time, let's say that you have your hardware platform, and this is supposed to be integrated in a more complex environment, like where you have some other electronic devices is sending you inputs. And in that case, for instance, if one of these devices is missing, you can use Spybuffers to emulate the interface, or also to inspect the data that is received by an interface without the need of processing it through the whole logic of your rest of your firmware. As an alternative, this is mostly jargon for people that are in the high-energy physics experiments, but this is also a powerful tool for data quality, because you can put these Spybuffers after some key parts of your firmware, and they will extract some key feature from your reconstruction algorithm, for instance. And this can be published to some database that you can use in order to make data quality plots and check that everything that your algorithm is supposed to do is behaving correctly. And last but not least, because in principle you can imagine many applications of this simple logic, is that you can have some automatic error handling. So for instance, if you have an error state, an error detection mechanism in your logic, this can be connected to the fast monitoring control block, and this can issue, for instance, the freeze command to all the Spybuffer and trigger some interrupt that then tell your server to just download a copy of all the content of all the Spybuffer that let people debug what is happening and can be just kept for the inspection. To moving to the conclusion, I want to mention this example, which is a dummy example with 2 blocks. These are just 2 firmware blocks that live in the data path, so they are connected with a faster clock, and the control path works with a slightly lower clock. And the dummy block master, this is generating a sequence of words in a loop, and the slave acts as a pass-through. So whatever is being generated by this, in the normal configuration, whatever is being generated by this goes through the SpyBuffer dummy 0, then goes through the slave, which will send data through to the dummy 1 SpyBuffer. And this is how it will look if you run this test. For instance, in this example here, this is done with the software, with the fast monitoring client that I was mentioning before. The freeze mode is requested on the first SpyBuffer, so the dummy 0, and the fast monitoring takes care of updating all the registers because in this project there are more SpyBuffer than 2. And if you read the content of the memory, you will see that this will print words in the right sequence, which would be bad B does fab did, repeated all the time throughout the memory. And this is frozen and accessible. In principle, you can also write the content of this memory. I want also to show that when this, just to remind you the application of this, when you issue the freeze mode, the logic of your data path is not interrupted because, as you see here, for instance, I'm reading also the SB dummy 1 after I wrote the dummy 0 with some call for coffee, and what the content of the dummy 1 SpyBuffer is still there, and you can see that the order now is a little bit messed up because the SpyBuffer 1 is not frozen in this stage, so it's been constantly overwritten by the logic. Finally, the playback mode. So when you have something that has been written to the first SpyBuffer, you set the playback mode. Oops. You see that the data gets replicated through the second one. So this was just to show a tiny example of this. If I move to one of the applications of this is one of the possibilities, and in the Atlas MDT trigger processor, which is one of the upgrades for the muon trigger system of the Atlas experiment, this is currently being used. And during the development stage, which is during these years, the fast monitoring is being used for the validation and testing of the firmware and the interfaces. But during the high luminosity LHC, this will also not be a tool for an expert that needs to do some debugging, but also some data quality production tool that will be made available. And just to wrap up, the fast monitoring and SpyBuffer are just a way to quickly, it's relatively a simple way to perform debugging of complicated firmware logic, and if you need an implementation, is available on this Git repository. This Git repo also contains the unit tests that are written in Python, and they use CocoDB, and they can also be used to regenerate the waveforms that are shown at the beginning. And that was it from my.
Thank you, Iacopo. Questions? On the left.
Should I ask? Yeah, this was very impressive work which you have done. But my question is always, what is the advantage compared to the debug tools which are provided by vendors like SignalTap or like ChipScope or internal signal analyzer?
So, for instance, I hope that I can cover all the aspects of your question, but I think that this gives a flexible way, and this is like something that is standalone and open source, if you want. So you can implement this in a very simple logic that then can be run on the SoC of these devices. So you don't need to use vendor-specific software that maybe needs to be compiled for different architecture and can be, and it's not maybe granted that this will be able to run on a small SoC that you have within the experiment for the trigger system. This is maybe one possibility. The other is that you can probably, I'm not sure, I'm not really sure about if with ChipScope you can manage multiple of these things, and you can also write content doing it in a systematic way, for instance with script. Probably yes, but it really depends on the implementation. I think that the main advantage is that this can be something that is helpful during the production. So when you have these things running, for instance, on a board in USA 15 under the Atlas control room, and this can be something, and you can have some automatic polling of the data from the Spybuffer published to something else. Of course, this is not the only way. I mean, multiple different implementations are possible.
In the back.
Can I ask first?
Yeah, please.
Yeah, if you go to the block diagram of the, even the Atlas one or the main one, so if,
you mean this?
Yeah, maybe. So if I show you the block diagram of a JTAG controller, right? It also has data bus, it has an instruction register, it also provides feature to stop, halt, freeze, and playback, right? Plus JTAG is an open source specification, right? That each vendor, of course, like vendor specific people do it their way. It's also a fast bus. It is also industry proven, right? So instead of not using JTAG, if I use something like this, again, I think it's similar to the previous question, but what are the advantages why you did not design something like on an open source specification like JTAG and came up with your own? What was the motivation or what were the shortcomings of that?
I think that for this, maybe I think that there are people in the room that are more expert than me, but I think that the advantage of this would be that this is a simple block that you can implement, and the number of and the resource usages are just limited to the depth of the memory. And for JTAG, you have to introduce some kind of buffer or some kind of memory in any case, no? Because you need to be able to read what you have. And in that way, I mean, what you're going probably to end up doing is something very similar to this. So, okay, this was not just to advertise this specific module, but it's just for the idea of and the applications in the high energy physics experiments.
Hi. Well, first of all, thank you for this amazing work. At my work, I have started to think about developing some real-time debugging system, and I think that you saved me maybe two weeks or more of hard work. So thanks. Only a little question. If I have understand well, you have to break the data path with these blocks between the master and slave. I have seen something related to monitor interfaces or monitor attributes. Are you using this, or it is possible to use this not to break the data path?
So, if I understood correctly, until your data path is sending this data through, for instance, from one part of your logic to the other, you can put a Spybuffer, and in that case, it will be ready almost out of the box. You just have to write the fast monitoring control path, which is not given in the repository because it depends a lot on the implementation. But I mean, the concept of data path and control path is that maybe is too much focused on the fact that you have in the end this is going to be all the content of one single gateway, and you have just the data path is just what your FPGA would normally do without the Spybuffers, and the control is it has to do with all that is connected to the Spybuffer and what you can use for monitoring.
Okay, so thank you very much.
Hello, thank you. Taking advantage of the slide that you have right now there. So if I understood correctly, you're having all the control through the system on chip, to the processor of the SoC, I assume, right?
Yeah.
So what are you running on the SoC? Is an embedded Linux or is a bare metal application?
I mean, in the specific application that we tested, this is done with an SoC that is running Alma 9, because it's the operating system that is currently supported by Cell.
With Alma 9? Okay.
This is a Xilinx Zinc FPGA in our case, and it's not talking directly to this is not living on the programmable logic of the Zinc. It's on another FPGA that is being accessed.
So it's an external FPGA. Okay, thank you.
I have one question myself. This is running on an operational system now, currently, or it's for the future?
It has been no. It has been used for some cases, but it's not running in production mode. So with the data quality.
Okay. And do you have an idea of what percentage of resources in the FPGA, in the logic park, it takes in a real design?
Yeah, this unfortunately is very difficult to estimate because it really depends with what you want to monitor and your logic. I think that in the backup slide I had just one example, but it's probably just, I think that, oh, sorry about that. I can re-upload the slides with that, but essentially the number of configurable logic blocks it has to deal essentially with the size of the buffer and its width, plus some other registers for implementing the MOOCs and the other few things that you have in the diagram here.
Okay, so if you are really constrained, you could.
You can, in principle, act on the number of the SpyBuffers that you want to insert, and for instance, if you have, maybe you can act on their depth. This really depends a lot on what you want to monitor.
So first, I wanted to make a comment, because I think there is a general kind of misunderstanding, because this is very different from JTAG. The idea, we all do something like this in the higher energy physics experiment, and the idea is that we keep this while it's running, and the data will be transmitted over the network of the experiment. So it's not something that you use in debug phase. You plug the JTAG, you see that it works, then you unplug it and you ship it where it works. So this is, as Iacopo was saying, in production phase while the experiment is running. Then I wanted to ask you, if you use this kind of things for data monitoring, for data quality, this means this is what we call in Atlas the readout is done with this Spybuffer?
No,
or is it an additional thing?
This will be an additional thing. So at the moment, this is used for debugging, but eventually, for the data quality, you may need to write a service that will run on your SoC, for example, and that talks via Ethernet to the central data quality services.
And then on top of this, you will have a readout.
Yeah, but this will be something that lives in the data path, if you want.
Okay. And then the other question is, it's true that the data path is almost free because it's just a multiplexer when you disable it. But have you experienced that multiplexer makes your timing any harder, or is it really smooth, like if it wasn't there?
You mean if this is meeting time constraints, or if
this like
just adds some delay to the
you make the timing, then you add the Spybuffer, and the timing is not met anymore.
I think that it may happen if you add many Spybuffer, and the clock difference between the control path and the data path is maybe in a particular way that essentially your logic doesn't meet timing. This can happen, but when it's like this, you can act also on the number of Spybuffers that you have, and you can check if this can be fixed.
Yeah. And the last one is, as you said, that is vendor independent, so the memory must be inferred. Have you got any means of deciding if it's block memory, ultra RAM, or?
So in some cases, this depends on the implementation, because the memory. So at the moment, if you go to the repository, there is a link to a file which is external because it's done in one of the Xilinx reference example for HDL, and but is implemented in pure logic. So when you do the synthesis and the implementation, then your FPGA will do something the software will take care of this. But for some cases, I think it was being done using Ultra RAM, but yeah. This really depends a lot on the hardware, I guess.
Okay. Is this a generic? Is this a generic of the Spybuffer module that you can configure?
You mean the type of normally you can do this configuration when you do the synthesis or implementation, if I remember right.
No, it depends on what you say on the file. Yes.
So maybe for this.
So in the instantiation of the Spybuffer, I don't know if there is a parameter where you can select the different type of RAM, and that is propagated down.
But this in general is including the memory is just described as registers. So I don't know if this is done at the level of.
When you copy that Vivado thing that you say is described, that one will generate block RAM if it's described in a certain way, and or it will generate ultra RAM. So maybe what you could do is add a switch that switches between the two implementations, and then put there a parameter that says block RAM or ultra RAM, and then switch between the two description. It's true that it described that by the way you describe it, Vivado will choose
one
which
of the
to
two
use.
in all the case, you mean?
Yeah.
Okay.
No more question?
Just on this same topic, you just need to add an attribute to the element that is storing the information to define it. So it's an attribute in a VHDL. And also, UltraRAM doesn't support 2 clocks, so I think it should be out of the equation for that.
Yeah, maybe for this I have to double check. I'm sorry about that.
Okay, let's thank Iacopo again.